So we're going to talk about nuclear magnetic resonance spectroscopy, or NMR, and this is a technique that's based on the idea that nuclei behave as if they were spinning about an axis. So we're talking about nuclei today. Most of the time in organic chemistry, we're talking about electrons, right? Today we're talking about nuclei. And so I'm going to draw a little scheme here. So if this is a nucleus, right, and you have a positive charge, right, because it's a nucleus, it spins on an axis, so it rotates. It's kind of like a rotating top, or like Earth rotates on an axis. And so I'm going to draw my axis here, where up is north, just like we have a North Pole on Earth, and down is south. And technically this creates poles, right? The North Pole is the negative pole, and the South Pole is the positive pole, but that's not too important. But what it does is it creates the positive and the negative mean that the spinning creates a magnetic field. So the positive charge I drew in that circle represents the positive electrostatic charge on a nucleus, and the north and south pole, the positive and negative there, are referring to a magnetic field. They're two different things, but the spinning, or this rotation of the positively charged nucleus, allows or creates this magnetic field. And so we can simplify this and think of those little nuclei as little bar magnets. They have a magnetic field, so they have a positive and a negative end. But the thing is that only certain nuclei are actually magnetic and behave this way. So I'm going to put a little bullet point that says that. The hydrogen nucleus happens to be magnetic. So we can do NMR, we can study the magnetism of the hydrogen nucleus. Another common one that we will look at in organic chemistry, but mostly second semester, is carbon-13. Does anybody know the most common isotope of carbon? Carbon-12, yeah. Carbon-12 is not magnetic, but carbon-13 is. And we can use carbon-13 to help us because there's actually a very small amount of carbon-13 in everything. So it's only about 1% of the total carbon, but it's enough that we can use it to measure things about molecules. Okay, so in solution, these nuclear spins are completely randomly oriented. So these little magnets, or if we think of the little arrow there as the north and south pole, those little magnets are pointed in all kinds of different directions. So it might look, you have a bunch of molecules or a bunch of nuclei, and their magnetic fields are completely randomly oriented. Some of them are up, some of them are down, some of them are sideways. So they're randomly oriented, and that's in fact why most materials are not magnetic, because their magnetic poles are random. They don't all go in the same direction, unless you apply a magnetic field. So if you apply a magnetic field, I'm going to draw this as if it's a reaction, so I'm going to put my arrow, right? I'm going to apply magnetic field. And so I'm going to draw my magnetic field here. I'm going to say that my magnetic field is up, or it's pointed like this. So this is the magnetic field that I'm applying to the solution. And when a magnetic field is applied, all of the spins are going to be parallel to that magnetic field. Some of them will be pointing in the same direction as the magnetic field, and some of them will be opposite of the magnetic field, but all of them are parallel or anti-parallel. So what a parallel spin would look like is now we've turned, the random spins to the ones that are going all the way with the magnetic field. So those are parallel spins. And there will also be anti-parallel spins that are opposite but still parallel to the magnetic field. So those are called anti-parallel. Brianna, do you have a question?
Yeah. Do you have them every other, so like up, down, up, down, up, down? Is that how they would be?
They're kind of randomly distributed, but all parallel or anti-parallel. So I'm not trying to show that they're coupled to each other necessarily. Okay. Now, after you apply a magnetic field and all of the spins are now either parallel or anti-parallel, you have a different situation than when you started with. When you started, all of those spins were randomly oriented and they all had the same energy level. But now when you've applied a magnetic field, the ones that are parallel to the magnetic field actually have a lower energy, or they're more stable, than the nuclear spins that are oriented anti-parallel. So we actually create an energy difference between the parallel and the anti-parallel spins. So I'm going to write an energy diagram here. Actually, first I'm going to write what I just said. Oops. So there's going to be an energy difference between the parallel and the anti-parallel spins. And the difference in the energy depends on how strong the field is. So I'm going to show you an energy diagram to illustrate what I mean. So on the x-axis here, I have increasing magnetic field going this way. So I start at 0 and I could go to whatever. And then on the y-axis, I have energy, or the difference in the energy. So I'm going to put 0 difference right about there. And at 0 field, your parallel and your anti-parallel spins are pretty much the same energy. So those two guys are going to have the same energy at 0 field. But as you increase the field, the parallel spins decrease in energy relative to the anti-parallel spins. And so you have an energy split that looks something like this. Right? So I could draw the anti-parallel and parallel spins at any given point. And the more you increase that magnetic field strength, the larger the split is. And this is where NMR spectroscopy comes from. So we apply a magnetic field to a sample, and we split the energy levels. And if just the right amount of energy is added, you can actually bump the red spins up to the blue, and then they can fall back down. And you can measure the amount of energy it takes to bump one up, and that tells you something about the nucleus. And it will actually allow us to determine structure of a molecule. The energy that it takes to bump one of those guys up is actually very, very low energy. It's energy in the radio frequency, right? So like we know visible light is, kind of high energy light, and then we have infrared, which is lower energy, and then the radio waves are even lower energy. So it's not a lot of energy that it takes here, but when you change a parallel spin to an anti-parallel spin, this is called putting a solution in resonance. So that's where the magnetic resonance spectroscopy comes from. So I'm going to So you all have an NMR in front of you. Check it out. All of the peaks that you see on that NMR are places where your nuclei have been put in resonance after a magnetic field has been applied. So you can see that there's peaks at different places, right? And that's because for each type of hydrogen that's in your sample, it takes a little bit different amount of energy to put it in resonance. And so the machine actually measures the absorption of that energy, or where that energy is absorbed. Now, the amount of, just some more theory, the amount of energy needed to obtain resonance depends on both the applied field, right, the applied magnetic field, because that, right, the applied field determines the distance or the difference in the energy. And it also depends on the electronic environment of the nucleus. So it depends on what else is around the nucleus. So those are the two things that are going to matter. Our applied magnetic field for our experiments doesn't change. So the one thing that does change and is going to give you the different positions of the peaks is the electronic environment around that nucleus. So when I say electronic environment, I mean the amount of electron density, mostly. So the amount of electron density really matters. So that's the first thing we're going to focus on. All right, so I've drawn a little molecule up here. I'm going to color in one of my groups of hydrogens red, and I'm going to label them hydrogens A. And the other group of hydrogens, I'm going to color in blue, and I'm going to call those hydrogens B. When we measure a nuclear magnetic resonance spectrum, oops, it looks kind of like this. So on the x-axis here, you have chemical shift. And that's usually given in units of parts per million, or ppm. And the funny thing about this is it actually goes from, it's opposite of what you're typically reading. So the 0 energy is down here, and then it usually goes up to around 10 or a little bit more than that. So on the far right here, you have low energy radio frequency. And on the far left, you have higher energy radio frequency. So if it takes more energy to put a nucleus in resonance, it will appear more to the left. This is kind of the opposite of what we're used to, right? We're used to reading from left to right. But knowing this, well, let's first talk about which one, A or B, is going to take more energy to resonate. Okay, so if we have no so I'm going to put 0 magnetic field here, right? This is applied field. And if we started at no energy difference and we go up and down, right? And so these are the parallel and anti-parallel spins. Let's say that this is your applied field that A feels. Does B feel more or less of a magnetic field than A? No, so sorry, maybe I didn't explain this well. There's actually, so each of those hydrogens is surrounded by an orbital of electron density, right? So when you apply a field, the hydrogen doesn't actually, the nucleus doesn't actually feel the entire field because it's shielded by this force field of electrons that actually repels the field. So whatever field you actually apply, none of the nuclei actually feel that entire field because they're all shielded somewhat by electron density. So let's ask this question. Which one of the hydrogens is surrounded by more electron density? The hydrogens on the methyl group, A, or the hydrogens next to a halogen, B? Hydrogens next to an electronegative atom. Which ones have more electron density around them? Remember that this is a polar bond, right? And it's pulling electron density away from the carbon. And so the carbon will pull electron density away from the hydrogens in turn. So let's try this again. Which one has more electron density around it? Hydrogens A or hydrogens B? Yes. And so which ones have a stronger force field? A or B? Yes, A. So which of the hydrogens feel more of a magnetic field? B, yes. So A, if A is here, right, if this is the magnetic field that A is feeling, B is actually feeling more of a magnetic field because it has less of a shield around it. So looking at that little diagram I just drew, which one is going to take more energy to flip its spin, to put it in resonance? Which one's going to take more energy to put in resonance? See which one has a bigger distance between the two different, the parallel and the anti-parallel spins? So what happens, or what you would expect here, is that A would come somewhere, actually anytime you have a methyl group, it usually comes somewhere around a ppm of 1 or 2. So I'm just going to arbitrarily put A here. And I'm going to say that B, whatever it is, it's of a higher energy, right? Or it's going to take more energy to put that thing in resonance because it's less shielded. So I can label my x-axis here with the energy of the radio frequency, but I can also relate this to shielding. So down at the low energy radio frequencies, or on the right-hand side, I actually have highly shielded things, or we can say this is high shielding, things that have lots of electron density. And another name for this zone up here is upfield. So that's kind of some jargon that chemists will use. They'll say that it's upfield, even though there's low numbers. Chemistry is so confusing with the language. I'm sorry. Every time I think about it, I get mad at the old dudes that made up all this language. Okay, so then down at the left-hand side, we have low shielding then, right? Because so these are going to be things that have less electron density around them. And they have low shielding and they feel more of the magnetic field, so their resin or the spins are split more. And this is called downfield. So because the B hydrogens have less electron density, they are said to be de-shielded compared to the A, and it's going to take less electron or less radio frequency to flip A than B, or to put A in resonance than B. So B is downfield of A, and B has a higher chemical shift, right? Because the chemical shift numbers actually increase. Do you see here how the chemical shift can tell you something about the electronic environment or the amount of electron density? So, let's just take a moment here and look at your spectra. Everybody here has some kind of a primary bromide, right? Everybody has some kind of a primary bromide. So everybody has a molecule. Everybody has a molecule that looks something like there's some kind of an R group, right? And then you have a CH2 group. Can you pick out, just based on the chemical shift, right, this whole R piece is an alkane, so they're just CH2 or CH3 groups. Where on your spectrum is that CH2 that's attached to the bromine? Can anyone give me an educated guess where that's going to be? Is it going to be most downfield or most upfield? Is it going to be most shielded or unshielded? Yeah, it's going to be your most unshielded group of hydrogens, and so therefore it's the most downfield peak that you have. And so all of you have a CH2 group that is giving you that peak that's at the highest number chemical shift. And there's actually a group of peaks, and that group of peaks actually comes from only one group of hydrogens, and that's what we're going to talk about in a minute. So let's move on to talk about the next topic. And here I'd like to talk about integration. So each unique proton gives a unique signal, or each unique type of proton. So if I give you an example of 1-bromoethane, first tell me how many types, oops, I put too many hydrogens there. How many types of unique hydrogens are on this molecule? The answer is 2. So the 3 hydrogens here are the same. They are all connected the same way, right, to the same carbon. So these 3 hydrogens are the same. So they will all give the same signal. So you wouldn't be able to tell the difference between those 3 hydrogens. And likewise, the 2 carbons that are on the other, the 2 hydrogens that are on the other carbon are the same. So these are chemically identical hydrogens. The 3 that are on the left-hand side are all identical, and the 2 that are on the right-hand side are all identical. And so the fun part about NMR spectroscopy is it doesn't only tell you something about the electronic environment, it also tells you how many hydrogens are giving each signal. So you can integrate the peaks and it will tell you. So this one has a total of 5 hydrogens, so the total integration of my spectrum should be 5. So if I redraw the spectrum that I had above, right, where I said that A was coming at a lower chemical shift than B, B actually only has, whoops, wait a minute. Am I drawing this the same way? Yeah. Okay, so this is A and this is B. So we said that B was going to be at a higher chemical shift, so B would be here, and A was going to be at a lower chemical shift. Which peak is going to have a larger integration, A or B? Which one has more hydrogen? A. So I should have a peak, if I said that A's peak was that big, maybe B's peak would be that big. And if I integrated this, right, if I integrate the area under the curve, it should give me 2 here, 3, or a ratio of 2 to 3. So the area under the curve tells you how many hydrogens are giving that signal. Yes.
What's on the y-axis?
It's chemical shift in parts per million, and so it's basic. Oh, I'm sorry. You're right. This is intensity. It's just intensity of absorption of the energy. So the chemical shift gives you the ratio, or the integration gives you, the integration gives you the ratio, and it tells you basically the number of hydrogens on each type of carbon. Now, what if I give you a molecule like this? in this molecule, I'd like you to look at it and tell me how many different types of hydrogens there are. There's actually only 2 types. There's the hydrogens that are attached to the bromines. I'm going to call those A. And then there's the hydrogens that are these CH2 groups, and they're all actually the same. They're the same because all of them are 1 carbon away from one bromine and 2 carbons away from the other. So if you were a little molecule elf walking around on your molecule, you wouldn't know the difference between the different CH2 groups. So I'm going to call those purple ones B. And so if I had a spectrum of this molecule, it might give me something similar to the one before it, except in this case A would be my higher number chemical shift, right? So I'd have a peak for A here, and I'd have maybe a peak for B a little bit more upfield. How many peaks or how many hydrogens are going to make up peak A? 2. Yep. So I'm going to have a little blip for A. If I looked at the integration here, it would be around 2, right? For B, how many protons are there? How many B protons are there? 8. So I'm going to have a much bigger peak for B, and it's going to integrate for 8. But I'll warn you, your instrument doesn't know this. It's often that you'd actually get a ratio here of 1 to 4, and you have to use some other information to know that you have to double it. So it doesn't necessarily give you the exact number. It'll only give you the ratio between the peaks, or the ratio of hydrogens on each type of carbon. Okay, so far from an NMR, we could tell something about the electronic environment, and we can get some information about the total number of hydrogens and or the relative ratios of the different types of hydrogens. And there's one more really important piece of evidence that you can get from NMR, and that is that from the NMR spectrum, you can tell how many neighbors one hydrogen has, or one type of hydrogen. And this comes from the splitting. Let's start on your page. Splitting is also called coupling, and it's based on the fact that hydrogens notice their next door neighbors. So if you imagine the carbons are the houses that the hydrogens live in. So the carbons that I'm circling in red here, I'm going to call those carbons A. Those guys notice their neighbors, these hydrogens. So the A hydrogens know about the B hydrogens, and the B hydrogens know about the A hydrogens. And they actually end up giving you some interesting patterns in the peak. So a peak is not usually just one smooth peak. It actually has some features on it. And this comes from the fact that the neighboring hydrogens each have their own nuclear spin and it affects the nuclear spin of the other things around it. Okay. So let's say I have a signal for A, okay? And that's my little, just like the silly little signals I drew up here. I'm just kind of drawing a little blip on a spectrum, okay? So pretend like that's a signal on a spectrum, or a perfect signal. But for the there's two hydrogens on B, and those two hydrogens each have their own nuclear spin. So their nuclear spins can either be both, let's say that they can be both up. One can be up and one can be down in two different ways. And both of them can be down, right? Or in other words, you can have both parallel, both anti-parallel, or one is parallel, one is anti-parallel, okay? And so it turns out that the groups of the hydrogens will actually split. So B will actually split the signal in A. So if both of the spins are up, well, wait a minute. Yeah. So basically this signal is going to be split here, 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 and here. So when both of them are parallel, then it goes one way, right? If both of them are anti-parallel, it splits the signal in a different way. And when they're both when they're opposite of each other, it actually doesn't affect the field. And so you end up getting, basically this signal is split into 4 pieces, but 2 of them are on top of each other. So you have basically 2 signals here that give you a strong peak in the middle and 2 other little peaks on the sides. This is called a triplet. And the signal actually ends up looking like this. So the ratios here are 1 to 2 to 1, normally for a perfect triplet, but you don't always see that. And so if we saw a triplet signal, we can infer how many hydrogens are next to it. So we know that if we knew that this was signal A, and we saw a triplet, we could say, oh, signal A has 2 hydrogens next to it. Because the number of hydrogens is always the number of peaks minus 1. Or another way to say it is that the number of splitting splitting lines for A is going to be equal to the number of neighboring hydrogens plus 1. So number of lines. So the number of lines for A is equal to the number of neighboring hydrogens plus 1. Right? So if we had 2 neighbors, then we get a triplet, 3 lines. So you can have doublets, triplets, quartets, and if you can tell what it is, then you can call it a doublet, a triplet, or a quartet, but sometimes they're really messy, and you just call it a multiplet. So if you're talking about something in your notebook and you can't tell what it is from the spectrum, just call it a multiplet. If you can tell it's a triplet or a doublet, then go ahead and call it that. But a lot of the times you won't be able to tell. Our instrument here is only, so you measure magnetic field in megahertz usually, and our magnetic field is only 60 megahertz, whereas a decent instrument is more like 400 megahertz. So ours is really old, but it's easy to take care of. That's why we have it.
So there's 3 lines because on these, there's 2 hydrogens.
That's right.
So
Yes, exactly. Yes. And so from all of this, we see that NMR can tell us about chemical shift. It can tell us about the number of hydrogens on each carbon. And it can also tell us the number of hydrogens next door to each carbon. So from all this information, you can actually pull out your complete structure of a molecule. What I'd like you to do now is read the little comic that I gave you. Notice that they split things up. They're showing, and I apologize that part of the right-hand side got cut off a little bit, but just look at the big arrow, the 2 big triangles with arrows on it. They're showing you that chemical shift in the yellow arrow on the left tells you about electronic environment. They're showing you that coupling tells you about the neighbors, and that the peak area or the integration tells you about the number of protons. So each of those little blurbs is color-coded for either chemical shift, peak area, integration, or coupling. And if you want to see I have a copy over here that doesn't have the ends cut off. But I'd like you to read that, and if you want to. But I'd also like you to try the problems on this worksheet. So I gave you a little worksheet. I'd like you to work through that problem set, and then I would like you to apply what you've learned to interpreting your spectrum. I want you to take your spectrum and decide what the structure of your molecule is. Okay, so Megan and I can help you. Just raise your hand or shout when you need help. Once you identify your molecule, you're done and you can leave. But it would be great if you could empty out the NMR tube for me and just rinse it out a few times with acetone before you go. And you're not going to be tested on NMR in lab, obviously, but you will be tested on it in lecture. Most, not the theory, but more about like how to use it or interpret an NMR to identify a structure. Okay? Do you want to try a worksheet?